Okay, welcome everyone to the second contributed talks session in PEPM'22. The first talk in this session will be by Friedrich, Bolz-Tereick, and Yusuke Izawa, and the joint work with Hidehiko Masuhara. They'll talk about generating different JIT compilers, tracing method-based, from one annotated interpreter, if I understand that correctly. So, and if you have any questions you want to ask after the session, please either raise your hand later or already put them into the Q&A tab on the right. Okay, then Friedrich, the stage is yours.
Thank you, Jonathan. So we split the talk into two halves. I mean, as Jonathan said, it's a talk about our short PEPM paper, two-level just-in-time compilation with one interpreter and one engine. And the first part of the talk, which I will give, is basically an introduction into the background technology that our current strand of researchers worked on. It's called RPython. And I will give a general brief tutorial or introduction into this technology. And then after about 15 minutes, Yusuke will take over and describe what our current research is, what we're currently working on. So let's start with that introduction. So RPython is a project that I've been working on since many years, and it's basically a language that can be used to implement interpreters. And it was specifically designed to implement interpreters. And RPython, the name means restricted Python, is a subset of Python chosen in such a way that you can statically type it. You can use a whole program type inference step to find out all the types that you use in the interpreter. So if you write an interpreter for your language L in RPython, you can find out all the types in the program. And then afterwards, through a series of transformations, you can take the interpreter in further types and transform it into C code. And then you can take that C code and compile it to a binary, and then you have a virtual machine for your language L as a native binary. And during this transformation step, a number of components are automatically inserted into the final binary. And the most obvious one is the garbage collector. Python is a garbage collected language, and RPython is also a garbage collected language. So a garbage collector needs to come from somewhere. And it comes, I mean, you don't need to write it yourself if you just want to implement a small language. Instead, you get it automatically built in as part of this complicated transformation process that takes your interpreter and produces a binary. Right. So which languages have been implemented with this language to implement interpreters and the most mature languages that we've implemented with this language, RPython, is called PyPy, which is nowadays actually a pair of language implementations. PyPy is called because it's a Python implementation of Python, a Python implementation in Python, in RPython more specifically. And it's a pair of implementations nowadays because we have both a Python 2 implementation and a Python 3 implementation. The Python 2 implementation is extremely stable and mature, and we don't really touch it that much anymore. We're still very actively working on the Python 3 implementation in order to try to keep up with the quite rapid evolution of CPython, the default implementation. And so those are the most stable and common ones, but then there have also been in the past quite a number of more experimental implementations of many other languages, PHP and Ruby, but then also more declarative languages like Prolog and Racket, as well as a quite experimental SQLite re-implementation. Okay. So far so boring, right? I mean, we have some weird language which can be compiled to C, and you can implement interpreters with it. That's not that exciting. And the thing that makes it interesting is the fact that in this transformation step, you can add another component into the final binary, and that component is an automatically generated tracing just-in-time compiler for your language L. And this is the thing that I mean, this is the reason why we're doing this project, right? Without this component, everything would not be that interesting. Right, so as I said, when you turn your interpreter written in RPython into a C binary, you can add a special switch to this process that does the transformation and say, I want a JIT inserted, please. And this JIT that will be inserted is a tracing JIT. And we use an approach called meta tracing, and what that is, I will explain in the rest of the talk. And meta tracing JIT is basically a general JIT that is just-in-time compiler that is parameterized by the interpreter that you're feeding into the start of the process. And the compilation strategy that just-in-time compiler uses is so-called is a tracing. It's a tracing just-in-time compiler. What does tracing mean? Tracing means that in order to produce machine code, the JIT compiler will observe what the interpreter is doing, will keep a kind of log what the interpreter is doing, and it will produce straight line machine code for one commonly executed path that a little bit of runtime profiling identifies, and take that straight line path, turn it into optimized machine code, emit it into RAM, and then you can immediately execute that a straight line piece of machine code. And of course, given that, I mean, we started mostly with imperative dynamic languages. That means that the tracing JIT compiler focuses its effort on loops, because loops are the thing that run for a long time, kind of by definition. Right, and given that it's just one path through the control flow of the program, we need to add some extra checks that make sure that the machine code still stays on that path. And these extra checks are called guards. And the guards are basically there to check whether all the conditions are still met, that make sure that we are still on that same path that we've also been on when we recorded the piece of, like, the trace, the piece of machine code. And if such a condition fails, if we want to take another path, then the guard will fail, and that means we will transfer control back into the interpreter and continue interpreting code from the exact same point. And then later we can decide that this side path is also interesting, and we can patch in a new straight line path that starts from such a guard. Right. So how does the meta thing work? Right. I mean, tracing JITs are relatively known and relatively well understood. So the question is, what is this meta tracing? And I mean, the cool thing about giving a talk about PEPM is that there's a relatively simple way to explain what meta tracing is. That's not, yeah. And meta tracing basically is a cousin or a variant of partial evaluation with a lot of very clear similarities and also some differences compared to sort of more traditional partial evaluation systems. And in some sense, it's a very standard first Futamura projection. It's a first Futamura projection that turns an interpreter into a compiler. And of course, there's one important difference, because it's a compiler that actually doesn't run ahead of time. It's not a source-to-source transformation. It's really it's part of the binary. It runs concurrently to the program that the L interpreter is running, and it's a just-in-time partial evaluation system, right? But as I said, many things are really completely standard partial evaluation things to do, and you separate in quite a standard way. The variables in the interpreter are separated into classes, the static variables and the dynamic variables. And then, as usual, the bytecode is static and the program counter is static. And all the variables in the interpreter that store the data that the program operates on is dynamic. And this separation of the variables into two classes is guided by a number of annotations that the author of the interpreter needs to insert into the source code of the interpreter. By that, I mean, the number of annotations is small. It's like a handful or a few dozens at most. And I've tried to sort of sketch them by adding these red stripes here. Right. So and then you proceed in a relatively normal PE fashion. You observe some operation, and if it's done on two static variables, then you can just constant fold it. And if it's done on a mixed static dynamic input or purely dynamic input, then you need to residualize it into the trace. Right. So that part is also very close to sort of traditional partial evaluation. But there are also a number of important differences to sort of more traditional partial evaluation systems. And one very important difference is the fact that this meta tracing system happens at runtime. That means it's interleaved with real execution of a program running in this interpreter for your language L. And that means it has one extra piece of information that a traditional PE system doesn't have. And that extra piece of information is values for all the dynamic variables. Tracing observes what the interpreter is doing, and it observes what a real concrete path through your program is doing. That means in addition to constant folding operations on static variables, it will also always have values for all the dynamic variables, and do some real execution of the program concurrently, like at the same time as producing a residual program. So that's one important difference. And the other important difference relates to control. So in a sort of traditional partial evaluation system, control is actually a very important component. And there's been a lot of research in the PE community about finding good methods to get the control of a PE system right, and like decisions about which calls to unfold and which to residualize, and sort of getting the balance between over and under specialization right. And it's actually in many PE systems a very delicate balance between the two, or it's completely guided by a lot of manual annotations. But yeah, it's definitely not simple. And in the meta tracing system, we solve the whole control problem kind of with a hammer. So we don't use any kind of complicated heuristics or anything. What we do instead is we follow the execution of a real program. We never compile any side paths. Eagerly, we cannot, because in order to compile, we need values for the dynamic variables, and we don't have them in side paths. So instead, we just very directly follow what a real path through the program has been doing. And of course, this is only possible by this system being a JIT system, because ahead of time, you don't really know what the really taken paths through the program are. And as a side note, this also allows us the implementation of an operation we call unlift or promote. I mean, there's usually, in many PE systems, have a lift operation, which forgets information. It takes a static input and turns it into a dynamic variable. But we can do the opposite, because we have values for the dynamic variables. We can turn a dynamic variable static by just observing the real runtime value. But I mean, that's not really the point of this talk, so I will not go into more details here. Okay, I will give a very short demonstration of PyPy, like the Python implementation using meta tracing. And demos of JIT systems are very boring, because usually you just run the same program twice, and once it's slow and once it's fast, and doesn't look very cool. So what we started doing is we started doing video processing demonstrations, because they're very visceral and give you a sort of good feeling about the difference. And what I've done here is written a completely straightforward implementation of the Sobel edge detection algorithm. It's basically a discrete gradient operator that just goes over the image and finds edges. And here's the code, and we don't need to go into the detail of that, but we will run it. And what I'm doing now is I'm starting this with CPython. It's now started, and it will take several seconds for the first frame to appear, because this is kind of the worst case, the worst thing you can do for Python, right? There's a lot of arithmetic operations, and you do it for many pixels, and so it just doesn't work particularly well. And I've been talking for quite a while since I started it, but the first frame isn't there. There it is. This is my second webcam, and as you see, we can't really talk about frames per second here. It's more seconds per frame, and so nothing really happens. Let's see whether we can be patient enough for 1 second frame. But if not, maybe my laptop is also a little bit... there's a second frame. Let's stop it. See, the computation of frames per second is also very confused here. And if you run the same thing in PyPy, that's kind of, as you probably expected, that's kind of the point. It's much more fluid, and it gives 15 frames per second. Despite my laptop being sort of busy with streaming and everything, you can sort of see the edges of my hand and my turtleneck and stuff like that. Right. So much for the demo, and with that, we're also at the end of the brief RPython introduction. And I want to conclude by going back to Andrei Klimov's fantastic keynote yesterday. But there was one point that I not completely disagree with, but disagree with a little bit. He made the point that compilers from interpreters by Futomura toolkit projections aren't killer app, because writing compilers is not expensive enough. And I think that's a kind of interesting point. And I want to say that, okay, what RPython tries to do is it tries to make JITs a lot cheaper. And it tries to make JITs reachable for underfunded or open source languages that sometimes are extremely complex and don't have a lot of money. Right, so RPython contains a practical meta-JIT based on tracing, and we have applied it to many different languages, and there are a lot of similarities to partial evaluation, with the big difference that we do it at runtime following a real execution path. Right, that was so much for my introduction, and that's it from me. Thanks, and with that, we hand over to Yusuke.
Yusuke, are you ready?
Hi.
Thank you, Friedrich.
Okay, so I'm going to share my screen. Just one, please. Okay, so yeah, so it's my turn. Thank you, Carl. Thank you, Carl Friedrich, for the very interesting introduction of RPython. So okay, in my presentation, so I'm going to talk about two-level just-in-time comparison with one interpreter and one engine. Yeah. So okay. Yeah, let's go. So in this presentation, firstly, we are going to talk about the folklore in JIT compile community, and we show how our findings will affect the folklore. Secondly, we want to propose adaptive RPython that can derive a much tighter compiler from one interpreter and one engine. And finally, we review an observation that aims to confirm our adaptive RPython actually works by writing a small interpreter with adaptive RPython and running a program with the language. Okay, so as an introduction, we show folklore that a JIT-compile community has been believing. A JIT-compile community has been assuming that a meta-JIT compile performs a fixed kind of JIT compilation. For example, if we plan to create a tracing JIT compiler, we build a specific interpreter that is designed for tracing JIT. Also, we plan to create a method JIT compiler. We build a specific interpreter for method JIT. Again, if we plan to create a threaded code generator, we build a specific interpreter for threaded code generation. Threaded code is a kind of code style, essentially containing code instructions of the opcode handlers. This technique removes the overhead of indirect branching. In this example, the bytecode program has only code instructions to the handlers for div, const I, and at. Okay, let's see the cases of specific metajits, such as RPython and TruffleGraph. For example, we can let RPython generate a tracing JIT compiler. Generated virtual scenes, such as PyPy and Topaz, have only tracing JIT compilers. Also, in TruffleGraph, we can let TruffleGraph generate a method JIT compiler. The generated VMs, such as TruffleRuby or Python, have only method JIT compilers. So the meta trace, however, the meta-JIT compilers are language agnostic. We are still bounded in language and strategy specific viewpoint. In a nutshell, a JIT compiler community has been assuming that RPython does a fixed kind of compilation strategy. But with our findings, we can go beyond the assumption. This means that we have found a way to better meta-tracing compiler to do several compilation strategies, like method compilation, threaded code generation, and so on. This is, in a sense, we have a meta-tracing compiler pretend to be a method compiler, threaded code generator, and so on. Here, in this slide, we are going to show our findings about meta-tracing JIT compilation. That is, by providing defined kinds of interpreters to the meta-tracing compiler Python, we can derive defined outputs. For example, when we pass an interpreter for tracing compilation to RPython generates a program which is compiled in tracing compilation. And when we pass an interpreter for method compilation to RPython, the RPython generates a program which is compiled in a method compilation. And more, when we pass an interpreter for threaded code generation to RPython generates a program which is compiled in a threaded code generation. In other words, by changing an interpreter definition, we can get different kinds of compilers. Here, we propose adaptive RPython that can perform multi-layer compilation. To put it simply, multi-layer compilation is a compilation strategy that where several optimization levels are provided, and at one time, an appropriate level is selected. Depending on profile information, a selected level can be changed dynamically. To realize such a feature, JIT-compile community have been paying much implementation effort. For example, we have developed each compiler from scratch for each optimization level. But by using adaptive RPython, we need to prepare only one interpreter definition, and several optimization levels are derived from the interpreter. The preprocessor of adaptive RPython generates a common interpreter and a bit different primitives for each level from a generic interpreter. The generic interpreter corresponds to one interpreter in the title. And adaptive RPython performs edge compilation with the corresponding generated interpreter. This is one engine in the title. Next, we show the overview of multi-layer compilation on adaptive RPython. Firstly, a language developer writes a generic interpreter with adaptive RPython. And we pass the generic interpreter and the information that describes which instructions should be transformed to the adaptive RPython preprocessor. Then, the preprocessor generates several interpreters. Please note that interpreter tracing, interpreter threaded, and interpreter method are different primitives, and they share almost all definitions with interpreter common. Next, we pass source code and information that describes which variables are static or dynamic to produce machine code. Then, in tracing compilation, adaptive RPython partial evaluation system chooses interpreter common and interpreter tracing to perform tracing compilation. And in threaded code generation, adaptive RPython T system chooses interpreter common and interpreter tracing to perform threaded code generation. Again, in method compilation, adaptive RPython chooses interpreter common and interpreter method. Here ends the overview of adaptive RPython compilation flow. Next, we briefly show how we drive the RPython engine to pretend to be a threaded code generator or method compiler. Before showing how we drive RPython, we again explain the overview of meta tracing compilation. Please look at the program that has such a control flow here. In this program, B represents a condition branch, D here is jump, and E has a function call, and F performs return instruction. A meta tracing compiler compiles a loop of a source code into machine code by monitoring the execution of an interpreter. So the tracing path will be like this, and the resulting trace has a linear structure. So in the resulting trace, it has only one side of a branch, and it ends up with jump instruction that is going to the beginning of the trace. On the other hand, in threaded code generation and method compilation, we not trace the one side and not end up at the jump instruction, but we traverse the entire method at once. Method compilation can be achieved as an extension of threaded code generation, so here we only explain threaded code generation. The idea of threaded code generation is traverse the entire method body and not trace the inside of the handlers. Here, we show how the tracer for threaded code generation works. Overall, the threaded code tracer traverses the entire method body. So jump instruction is not tracked, but the tracer jumps to another branch. And the tracer does not trace the inside handler, but leaves the call instruction. After traversing the method body, and then when reaching this return instruction, the tracer for threaded code generation ends up traversing. After traversing, to restore the original control flow, we cut and stitch the generated linear trace. Finally, we can get a trace tree that covers the entire method body. And we realize this technique by tweaking the interpreter definition that is originally designed for tracing compilation. We will show the brief details next. Okay, so here explains the tweaked interpreter for threaded code and method compilation. Okay, we call this technique method traversable interpreter. These are the example code. The idea of method traversable interpreter is just to traverse steps firstly the method body with the help of traverse stack. The first key point is to decorate every handler don't look inside to suppress inlining. The annotation don't look inside is provided by RPython, so we can realize it very easily. The second key point is in jump if that corresponds to a back edge instruction. We use traverse stack to save other side of program point to traverse later. And the third key point is in jump and return instructions. Those correspond to a function and method end. Okay, so in jump to jump on the side, we already saved a program point to traverse stack, so we need to retrieve. So in this point, we need to retrieve that program point, already saved program point. So those codes are doing that kind of behavior. So if the traverse stack is empty, otherwise we finish traversing all passes by putting finish operation or return operation. Okay, next we show how we generate interpreters, including a method traversable interpreter. The idea is to embed tire-specific definitions in a meta tracing-based interpreter. Okay, so firstly, we declare G-tire driver at the top of the interpreter. Okay, secondly, we define can enter tire, blah, 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 for tweaked instructions such as jump if, jump, and red. Okay, thirdly, we write tracing the specific definition inside can enter tire 2. Finally, the processor generates several interpreters, including method traversal interpreter from this definition. Okay, that's all we have to say about the overview of adaptive RPython. Next, we'd like to move on to the observation to confirm the adaptive RPython system actually works. Okay, to confirm our findings actually work, we explain our observation. So in this observation, we implemented adaptive RPython and wrote an interpreter for small language called TLL. And we ran several applications on the interpreter. The applications are Loopabit and Colabit. And Loopabit is designed to confirm our findings can work on a nested loop. But time is limited. We skip the detailed result of Loopabit. Colabit, on the other hand, is created to confirm a much higher compilation can actually work. Okay, so we'll show the situation and results of Colabit in next slides. Note that our current implementation is work in progress, so the much higher compilation is tool level. It means that in this observation, we combined of the two. So that one is threaded code generation, and the second one is tracing compilation. Okay, so next we show the situation of the Colabit observation. In Colabit, there are two functions, the function f and function z. The function f is suitable for threaded code generation, and function g is suitable for tracing compilation. And we compare 5 cases that have different optimization levels. And the first case is Colabit based on interpreter. In this program, we apply threaded code generation to f, but function g is interpreted. And Colabit based on only we applied threaded code generation to both f and g. Furthermore, we increase the optimization levels, like changing the JIT compilation strategies. So Colabit tracing baseline is the pair of tracing baseline, and Colabit baseline tracing is a pair of threaded tracing, and finally, Colabit tracing only is a combination of tracing. Okay, next we are going to show the figures that illustrate the running speeds and trace sizes. So let figure illustrates the running speeds of adaptive RPython on Colabit. Okay, from the left figure, we confirmed that our approach actually worked, since by increasing optimization level, the speed is reaching to tracing JIT only strategy. And from the right figure, we found promising signs that much higher compilation here. This is a combination of baseline and threaded. Baseline and tracing compilation can reduce the compilation code size, since the running speed is same to tracing only, but the compilation code is about 30% smaller. So we thought that it will lead to get a good performance in the future. Okay, so let's conclude this presentation. In this presentation, we proposed adaptive RPython that can perform multi-style compilation with one generic interpreter and one single RPython's meta-tracing JIT compilation engine. For example, by choosing the generated iCommon, iMethod, adaptive RPython can perform method compilation. And the important point is that we confirmed that the adaptive RPython system actually worked by the observation with a small language and a program. Okay, in future work, first, we are going to decide the multi-tier comparison strategy. Okay, currently we design several optimization levels separately, but we cannot smoothly shift between each level now, for now. So we need to implement such a level moving and level deciding mechanism in the future. And the second future work is to implement our proposal on PyPy, and we are going to measure the impact with many benchmark programs. That's all. Thank you.
Thanks a lot, Yusuke, and also Karl Friedrich, for the very interesting talk. While we wait on other participants to write their questions into the Q&A, maybe I can start with a question already.
Okay.
Could you characterize in which cases meta tracing does not perform well, so the assumption of your work is that sometimes it's not ideal, I guess, because that's why you explore also other approaches to JIT. But could you maybe characterize more under which conditions meta tracing doesn't work so well?
Yusuke, if you want, I can try to answer that.
Please.
So I think there are two situations. One of them is that very early in the lifetime of a program, I mean, so tracing sometimes takes too long to sort of warm up. And that's why we're concretely looking into this threaded approach, where we try to sort of have a bridge between purely the interpreter performance and the eventual performance of a warmed up sort of fully connected nest of traces. And then also very late, like so very late in the lifetime of a program. Sometimes you have these really big, complicated nests, and it would be better to have a kind of more global view of them and have a way to optimize them more globally. And that's where we kind of know some problems are, but we don't completely know what to do about those yet.
For briefly speaking, we can find such worst cases in the recursively style written fib. So we call such a problem path divergence problem. When tracing in such kind of program, we fell into the creating many bridges, but many guards are failing. So many controls are going back to the interpreter, so the performance will decrease.
And in this cases, you would like to switch to
yes,
method-based JIT or something?
Yes, method-based
exactly.
or threaded code. Yes,
Okay.
absolutely. Yeah.
Okay, great, thanks. Are there any questions from the audience? Actually, I can't see when somebody raises their hand, but I guess this is being taken over by the student volunteers. Otherwise, I also do have another question. You talked about method traversal, about the method traversal interpreter. And do I understand correctly that the premise of this technique is that you want to reuse the existing trace-based JIT, which is a part of RPython, instead of writing again some method-based JIT implementation?
Yes. So we don't create a method-based compiler from scratch, but it just drives the RPython engine to track the entire method body. So the key point is just the usage of traverse stack. So it's kind of a trick, and it's kind of a trick to have the RPython engine to pretend to be a method compiler. So
you basically try to explore more paths than this one that trace-based JIT would explore, right?
Yeah. So devs firstly traversing.
Yeah, I see.
By using traverse stack.
But I have another question, follow up on this. Carl Friedrich said that you compute in parallel on an abstract and concrete values. How does that work for this? Because you don't have concrete values here, right?
That's exactly the you hit one of the cores, basically. Yes, I mean, in one interesting way to view this is that, I mean, usually in a PE system the control is part of the PE, but now we're moving it into the interpreter, right? In the interpreter we say, oh, we have these things, and indeed we don't really perform the operations, right? Because we do not have values. So we just use this to sort of produce these calls, and then later we sort of rearrange the trace a little bit, and then we can actually run it. And so that there are a little bit two modes. There's a mode that we use to sort of explore all the paths, and then there's a mode where we actually run things, and then the operations actually do something, right?
Okay.
But yeah, I mean,
yeah, it makes sense. A bit difficult to understand right now, but yeah.
Yeah, sure. No. But I mean, this is really one of the key points. So I think it's great that you hit on it, because it means that we got some things across. So
yeah, are there any questions from the audience? I can keep going asking.
Oh yeah, please.
But let me look at my notes that I took while you gave your talk. Oh yeah, I also have a question as a user of your system. So you talked about you put annotations on this one interpreter, right?
That means user in the sense of you're writing an interpreter.
Yes, so I'm the one that wants to implement the language and I want to generate my JIT compiler with it. Can I make mistakes that actually lead to bad code, like actually semantic errors, or
so there are two kinds of mistakes. There are two kinds of mistakes. There's the bad kind where you really manage to get miscompilation. That's relatively hard. The main annotations that you could use to do this is we have an annotation that says this function is pure, right?
Okay.
Because we cannot always use that.
Yeah.
And if you misapply that, then then the machine code that you produce at the end will do different things than your interpreter. But then otherwise, the mistake, quote unquote, is, I mean, the usual working style is that you start with a slow JIT, and then over time you sort of add some more strategic things, or you rewrite your data structures a little bit, and then over time you get a better and better code. That's kind of the working style. And you do that by adding some annotations. Like sometimes, for example, sometimes you have an immutable data structure, and we cannot infer that in all cases. And so you would say that this thing is immutable, and that means if we have operations on an instance of it, we can constant fold all reads, and then the trace will get a little bit better. And sometimes you also might have to like rewrite the interpreter a little bit, right? That's like in a PE setting that would be like binding time improvement. You separate sort of the static parts of your data structures from your dynamic parts, and then all the operations on the static parts can get constant folded, and the dynamic ones remain. And I mean, one of the nice things about it is that it's this sort of very incremental process, and you can stop at any time, right? You can say, I'm happy with the state and the performance is good enough, or you can spend years to sort of come up with new ways to express things that match tracing better, like meta tracing better. And this is the state that we're in with the Python interpreters. Because for the Python interpreters, a lot of the work is really to sort of come up with better ways to sort of structure all the. I mean, Python is a very big and complex language. And so a lot of work goes into sort of structuring the internal runtime data structures that you need to express all the different kinds of values that you can have.
Yeah, makes sense.
You need to specialize them for the typical use cases, right? That real programs use.
Okay, great. I have more follow-up questions, but
Yep,
now
I mean,
we're running out of time. Maybe
let's
you can
go
take
offline.
more offline. Yes.
That was a great discussion.
So
Thank you.
thank you very much for the interesting talk again. And yes, let's thank